We're going to draw Lewis structures for these molecules, indicate the polarity of the covalent bonds using these Greek symbol delta positive, delta negative to indicate their polarity because they're not fully charged, but they're partially charged. And that is because one of the atoms sharing the covalent bond is more electronegative than the other one. In other words, atoms that are generally higher up and to the right of the periodic table have a greater affinity or a greater attraction for shared electrons. Let's get right into letter A. You might be more familiar with it written H2O2, that's hydrogen peroxide, but they're giving you a hint on the structure. We don't need that hint because we know hydrogens are never the central atom. Let's count out the valence electrons. Hydrogen contributes 2 because there's 2 of them. Oxygen is group 16. That means it has 6 valence electrons and there's 2 of them. That's 12 plus 4. We got 14 valence electrons to work with. Put oxygens in the center, hydrogens around. Put a bonding pair between each of those atoms. That's going to eat up 2, 4, 6 electrons. Bonding pair is a pair of electrons in a covalent bond. So we are down to 8 valence electrons. Let's get the octet on the terminal atoms. Terminal atoms are hydrogens, so they already achieved the octet rule by getting a duet. Now we can put the remaining 8, distribute them evenly around the central atoms. And there we go. Now we know this is not a linear molecule because we learned in VSEPR that if you look at the central atom here, this has 1, 2, 3, 4 regions of electron density. So this is tetrahedral with bond angles of 109.5 or around that degrees. And same thing here. In other words, it is not a linear. Let's try to draw this a little bit better. Down here, there's an H, there's an O. Maybe put 2 of the lone pairs up there. Put 2 of the lone pairs as far away from the other lone pairs like that. And something like that without going into 3D mode. This is a little bit more accurate. All right, we already know behind fluorine, oxygen is the second most electronegative element. So when these pair are shared, oxygen is going to share unequally. They're going to be residing on oxygen side slightly more. So this side is going to be slightly more negative. And hydrogen losing some of that is going to be slightly more positive. And the same thing over here. Electrons are going to gravitate more. I shouldn't say gravitate. And there you go. Moving on to B. Let's go. Bromine and chlorine. They're both halogens right there with 7 valence electrons each. So we have 14 total valence electrons to work with to draw their Lewis structure. Doesn't matter which one you put on which side because there is no central atom. But let's connect them with the bonding pair. That's going to use up 2 of our valence electrons. So we're down to 12. Let's get 6 on each, and that'll complete the octet for each of them. So there's our Lewis structure. All we need to do is look at their difference in electronegativity. What do you think? Chlorine's higher than bromine on the periodic table. All right, so you should predict that chlorine is going to be the side that has the slightly negative charge, and then bromine is going to lose some of the electrons partially, so that side will be partially positive. All right, right there. The trend is up and to the right. On to C, hydrogen and bromide. There it is, 2.8, 2.1. Need a bonding pair, get this guy 6, and then this side is going to be, since bromine is more electronegative, we do like that. And our last one, let's go with purple. H2O. right? From biology, you should know this without looking at any reference. H2O is a bent molecule. Now we know why, because of VSEPR. Right, so these are all, this is actually 104.5 because of the extra repulsion from the lone pairs. Okay. Oxygen, very electronegative. That side gets a slightly negative charge, and this side, there you go.